Okay, good morning. This is IRTF Open. It's the first of two sessions this week. So we want to dedicate this session to a discussion about internetworking research challenges for AI. So we put this together in a cooperation. So this is Antoine Fresnancourt, who helped with the organization, and I'm the Kutscher, the IRTF chair. And quickly before we get started, so you already agreed to this when you registered for the IETF, but so we are operating under the IETF IPR rules. So let us know in a short time if you are involved in any IPR activities or you see anything in this direction. This is going to be recorded and also streamed live. And there are a few rules regarding privacy and code of conduct. So yeah, please observe the IETF code of conduct and anti-harassment procedures, and also the special IRTF code of conduct, which makes additional statements about ethics and research and a few other things. And yeah, please use the Meet Echo tools and the queue management system for the later discussion. Yeah, quick reminder. So I think this is in particular in order since the topic is discussed so widely and intensively this week. So there's a lot of stuff going on AI, agent communication, and so on. So we are here at the Internet Research Task Force. So nothing that we do will result directly in standards. So we're doing research. We want to enable experiments and then gain insights that could potentially later inform IETF standards work, for example. So that's why we are often yeah, not so much concerned about short-term standards or engineering solutions, but like bigger research challenges. And this is also a little bit the spirit of this meeting. So we will have AI note-taking as well, but nevertheless, we need a note-taker in the room who could capture the gist of the discussion. Can we get any volunteer? Ah, thank you very much. That's great, thank you. So we use the online note-taking tool. Anybody is welcome to chip in additional observations if they want. Okay, so why are we holding this meeting? So, well, we have been discussing, research challenges for networking for AI for quite a while. So we had side meetings on this, and it's obviously one of the major topics in networking and distributed systems research at the moment. So the goal of this meeting is to further discuss and find out what could the IRTF do constructively in this field. So what would be a good role for the IRTF? What would be good topics? And so, well, as these systems get more pervasive, more distributed, more deployed in different scenarios, not only proprietary data centers, questions arise as to how would this be related to internetworking, protocol engineering, protocol design, but also maybe to new approaches of how to see the overall stack in this field. So, for example, the intersection of distributed computing and networking. And so we hope we get some more insights and also with your help discuss this a bit further. And yeah, then potentially come to some conclusion in the near future. So if you're not aware, there was a previous ACM CoNEXT workshop in December last year that we organized, and I think it went pretty well. So had really diverse presentations from different companies, different academics working in this field. And well, I left that workshop with quite good confidence that there is really interesting research to be done in this field. Okay, so this is the agenda for today. So we have 3 talks. So one by Mingxin Chang on disaggregated architectures for large model inference. One by Hong Xu on reliability engineering challenges in networking for AI. And then one by Lixia Zhang on AI agent networking. And as you can see, we left quite a bit of time for discussion. So after each of these talks, of course, we'll have the usual Q&A. But then at the end, we hope to discuss the overall topic with you. And I'm looking forward to your suggestions and your comments on in this direction. Is there any other suggestion, any need for agenda bashing? Great. Okay, then I bring on the first speaker in just a moment. Mingxin, can you hear me? Okay, good. Just a second. Okay, thanks very much for coming.
Okay, thank you for the invitation. It's my honor to present here. So typically I'm from the distributed system community, and now our distributed system is more and more related to the network. So it's my honor to present some of the new challenges and how we solve it in order to enable disaggregated architecture for the large language model inference. So you know that just, last day or this day morning, it is GTC 2026, and the Jason also speak that nowadays we are in the era of LM inference. Now with the growing of so-called LM agents, where the cost in the inference field are much, much larger than the training, because typically from the beginning of ChatGPT, we are just chatting with the AI, which essentially is a singleton response and the short inputs and the short outputs. But now we are using agents. Typically an agent such as the OpenClaw or Manus, something like that, will execute a multi-turn and very complex execution of the interaction. And in each of this interaction, it will have very long inputs to gathering all the context needed for inference the corresponding output. And the output, due to the syncing pattern, it may always sync a lot, maybe 1K or 2K tokens, and then output the final result. And this complex and this difference has made the result, which is currently the inference cost, become much, much larger than the training cost. And now we are focusing on how to reduce the inference cost, because you know that in order to have a higher intelligence, the LM researchers are typically relying on the so-called scaling law. And the scaling currently we scale 3 main factors. First is we gathering more high high quality data. The second is we train the larger models. And the third is we enable a larger context. Typically, because we are currently using the agentic work, its context will be higher than 64K or even 128K. So it is much, much longer than the original cases. But this kind of scaling not only bring us a higher intelligence, it also brings us about 3 challenges. First is lack of GPU supply. Even though that currently we are still increasing the supply of GPU, but it is still not very enough. And the second is higher inference cost. Now, if you are raising some open core in your laptop, you know that the tokens are still very expensive. And the third is longer response time. So we want interactive response, but currently maybe one task, you give it one task, it might return 10 or 20 minutes later because the longer response time. So the problem becomes very apparent how we can improve the inference MFU, how we can maximize the flows utilization of our GPU. And the second is how we can reach these goals without sacrificing the user experience. Because if we increase the MFU, but at the cost that each request will only output 10 tokens per second, it will lead to even longer response time, and that is not the user desired. And one of the most important solutions that we can use heterogeneous hardware. For example, in China, we have 2 kinds of GPUs that are both based on something restrictions. First is H800. It is better for T-Pros, better for computation. And the second is H20, which is better for bandwidth because its computation is restricted. And also we have traditional the DRAM and the LPDDR solutions attached to the CPU. They are bad at the capacity because even though that currently the DDR is more expensive than last year, but it is still less expensive than HBM. And this is just a demonstration. With the growing of the hardware community, there are actually even more heterogeneous kinds of heterogeneous hardware. For example, today's GTC, Jason presented the LPU, the clock-based solution is best for bandwidth. And originally, they have presented the CPX solution, which use GDDR, not that good at bandwidth, but with a lot of T-flows, which is very good at computation. So how we can use different dimensions that are presented by different kind of devices is one of the main goals to enable this disaggregated architecture for inference. And this is possible because there are 2 critical properties of the large language model inference. The first, it has 2 different stages. One is the prefill, which we used to optimize for the first time to first token, TTFT. And because it parallelly process all the input tokens, it is very computation bounded. And the second is the decode, in which stage we will optimize for the time between token, TBT. And in this case, because of the auto-regression nature of large language models, it will output 1 token by 1 step. It consumes a lot of bandwidth, and because of the long context, it is to a lot of KV cache. It will also consume a lot of capacity of the memory. So one stage, the previous stage, consume computation, and one stage, the decode stage, consume bandwidth. And the second property is that we have KV cache. You know that also because of the auto-regression nature of the large language models. Also, actually, every token will only attention for all the tokens previous to it, not any token later than it. So if two requests, they share the same prefix, they can directly they can skip the computation of these shared tokens and directly reuse the intermediate result produced before, which we call it the KV cache. And because that currently we are using, again, the agent, the cloud code, the open cloud, all these will try their best to preserve the prefix. So even though that I see that for currently every request will have 64K inputs or even 128K inputs, 80% or even 90% of the prefix will be the same as the previous turn. So the KV catch hit ratio will be very high, as high as 80% to 90%. So reducing KV catch is one of the most important solution that we can reduce the cost of inference. So with all these properties that is natural to a large language models, now we can naturally use different hardware for different stage in the inference. We can use the device better for computation for the previous stage, such as H800, such as the CPX solution. And we use the device better for bandwidth for the decode stage. And we use the device better for the capacity, the DRAM, the SSD, for holding a lot of KV catch for future reuse. So based on this basic idea, we have made a very flourish open source community, which is called Mooncake. So the left part is an architecture of the Mooncake. It currently, based on a lot of hardware, can manage a very complex network topology and contain a lot of functionality and supporting different kind of other communities in the inference. And we are honored that just in this month, we have also officially joined the PyTorch ecosystem. We are currently with close collaboration with a lot of other communities that are also in the Torch community. And this project is initialized based on a collaboration with me at the Tsinghua University and the Moonshot AI, who is the producer of the Kimi K2 and the Kimi K2.5 series of model. And this is currently one of the SOTA models in the open source weighted large language models. So it is very important. And due to at the first day that Moonshot AI and the Kimi are obsessed by the long context. So we have experienced the challenge that we have mentioned before much earlier than other providers. And based on these challenges, we have made 3 contributions in our proposed Mooncake architecture. The first is the PD desegregation. Even though that the openly published paper, we are not the first that published the idea of PD desegregation. It's based on Microsoft and Peking University. We are the first that openly report that we have successfully deployed a very large scale PD desegregated LM serving architecture. And the second is that we made a KV catch centric architecture that make using pulling all the DRAM of all the GPU servers as a very large memory pool to holding all the KV catch to enable to maximize the reusement of the KV catch. And the third, we have made a lot of scheduling policies that are specialized designed for this kind of scenarios. And I will discuss this one by one. The first PD desegregation, as you can see that we use different device pools for different kind of stages. And originally, this PD desegregation is only used by the Moonshot in the real production. But now it is a standard score because now we are using a lot of very large language models initialized by the DeepSeek and later by Kimi K2 and the K2.5. They are terabytes level large language models. And in this case, you typically will need a different kind of parallelism strategy. For example, we will use a small parallelism strategy such as TP8 for the prefill. And we will use large EP, also called wide EP parallel strategy for the decode space. So this desegregation not only bring us the benefit of take advantage from heterogeneous hardware, it also give us the flexibility to apply different strategy on different stages. So this is currently become the status quo of serving large language models. And the second is the KV catch. The size of KV catch is actually very huge. Originally, we see that we need a lot of VRAM because we have large models. But actually, the KV cache is the true killer of your HBM, because currently the KV cache will grow linearly with your context length. It will grow linearly with your model size, and it will grow linearly with your batch size. So as a result, it will grow much faster because all these three input parameters are growth. So we may, in a real production, we have terabytes or even petabytes of KV cache that is reusable. So we need a very huge memory pool to store it. And gradually, actually, Mooncake not only used for PT desegregation. As you can see in the middle, we have a Mooncake transfer engine for PT desegregation, transferring the data from the prefill stage to the decoding stage. And we also use this Mooncake transfer engine to share the KV cache, transfer the KV cache from the DRAM, the SSD, to the inference engine. And now we are also building Mooncake Elastic EP, which we are used for the EP parallelism communication. A lot of different kind of solutions are all based on this kind of transfer engine. And the core component of Mooncake is its transfer engine. So it is highly related to the network. How to use this kind of network is one of the most important challenges for us. And now, it is not only academia paper that has received a best paper reward at UCNext Fast. It is also a widely deployed system in maybe the Moonshot AI, the Zhipu AI, the Alibaba, the Huawei, the NVIDIA. A lot of different companies are using this transfer engine in maybe not hundreds of thousands of GPUs, not if it is not millions or even tens of millions of GPUs. And it is integrated with two famous inference engines. One is VRM and the other one is SGLang. They are all both based on our transfer engine to orchestrate their distributed inference. So you may know that originally both VRM and SGLang are best for single machine, multi-GPU scenario. But now, as we have discussed, we need distributed service. We need disaggregated service. So they need a network orchestration layer, and they are collaborate with our community to make this possible. And also we have collaborated with the Dynamo system from the NVIDIA to standardize this part of the network communication and the distributed orchestration. So in the second part of my talk, I will briefly talk about what is the Mooncake and what we are building for the next version of Mooncake. So first, it must transfer very fast. And the second, it must store more KV cache as possible. And the final part, as a widely used library, it should be easy to use. So the first part, the transfer engine, we take advantage from the topology of multi-NIC topology. So you are not only make use of one network interface card. Every machine now have 8 network interface cards. You should pour them. You should make use best of the aggregated bandwidth. And because the aggregated bandwidth is so high, you must reduce your CPU cost as much as possible, because otherwise you will be bounded either by the CPU contention or by the local DRAM. So we are obsessed by the zero copy feature. We ensure an end-to-end one-time copy. So only from the source to the destination, only one copy, no intermediate result. And the result is that we are much faster than existing solutions such as TCP-based solutions or Zhilu. We are based on the RDMA or even GPU direct RDMA. And the second is that we pull the whole DRAM of we gather all the GPU, the DRAM from all the GPU servers, and now we are extending to the SSD devices to all the GPU servers in order to have a very large pool for a lot of KV cache, and use this KV cache to reuse across different turns of your agent to make best use of them. And finally, we just provide very simple, easy to use API, only put and get, very similar to a Redis key value store, but it is zero copy. So it will give you directly pointers to the source of the memory blocks and pointers to the destination block, and we will ensure a zero copy transferring. And I think this is different from the existing solutions. So this is the basic code of Mooncake, and as you can see, we enable 500 increase in the SLO aware throughput, or we call it the good put of the serving inference throughput of the Moonshot AI. And but this is the first version of Mooncake. After 1 year or 2 years of a large-scale deployment, we found that we are facing a lot more challenges. And the first challenge is that we are currently, the network is also heterogeneous. We have RDMA, cross machine, and we have intra-rack, which is, for example, the NVLink. And we currently have different kind of GPU vendors, and each vendors produce a different kind of interconnects. So this kind of heterogeneous become a new problem that we need to solve in the next version of the Mooncake transfer engine. And the reason is that in our original design, we have choose, for simplicity, we have chosen a so-called imperative pattern. At the start time, it will be statically binding to a certain protocol, whether your transfer engine wants to use RDMA, whether your transfer engine wants to use NVLink. But now we want a binding, a fusion of all these different kind of network channels. And the second, because originally it is still deployed in silos, one silos. Each silos will not contain a lot of GPUs, so the reliability is not a very huge problem. But now we have wide EP, we have a lot of GPUs very connected with each other. So the so-called Brewster diagram, or the diameter, the Brewster diameter become very large. If one GPU is crashed, it will take over, it will cascadingly make a lot of GPUs stop working. So how we can ensure the fault tolerance, ensure the resilience become the second problem that we need to handle. And these are several explanations of these problems. So as you can see, we originally either banded to NVLink or banded to RDMA, but currently 2D GPUs have multiple paths. We want to make use of the aggregated bandwidth of all these paths. And the second is the state brand scheduling, because that we will evenly slice all the payloads into fixed chunk size, and we scatter all this chunk to different network cards in order to make use of the aggregated bandwidth. But there are always stragglers, so the bandwidth utilization is not as good as we expected, especially on the later part at the long tail. And also the resilience become a problem. If one network interface card is crushed, because we still have 7 left, we still want the communication to available to the upper layer applications. But originally, we were directly with an error, and the upper layer engines also do not handle this kind of error, and it will crash, and we need a full restart. And that is not desired now. We need a more resilient solution. So based on these new challenges, we are currently actively developing the next version of transfer engine new technology, transferring engine. And its basic idea is that we actually made a unified segment abstraction. We unified all kinds of resources, the DRAM, the VRAM, the SSD, into memory segment, because all these different kind of memories or even disks can be addressed by a memory buffer and randomly accessed. So we, even though they are provided by different devices, we treat them logically identical as a memory segment with random access capability, and we register them into a global namespace. So this unified this unified abstraction provides us the possibility to have a better orchestration of the heterogeneous software. And also, in the first step, we will automatically probe the hardware information, and then we will map all the different network interface cards to each of the memory segments. So with NUMA aware and a lot of other PCIe root complex aware. So with this topology aware, we will choose which network interface card if it has the best affinity, which will be the best. But even with the best, we still enable different kind of fallback, a lot of fallback routes. So if the best is not available to you, you can still use the second route. And if the second route is not available to you, you can still use the third route. And in this new implementation, each route can be bounded to different protocol implementation. For maybe the best route is from the NVLink, and the second best is from the RDMA, and as a fallback, we can still use TCP if there are some disaster in the RDMA network. And this is the first. And the second is we enable a dynamic per request orchestration. I think that this idea is actually very similar, very popular in the traditional data center protocols. You have packet per packet routing. Each packet in your TCP stream will be routed independently. But in original implementation of our transfer engine, we will have a static binding of the route. So if that route is not available or that route is become congested, it will lead to a very low performance. But now in the new technology, we again in the upper layer, we also enable a dynamic telemetry driving adaptive scheduling. We will continuously probing the current load of each route and try to split the stream into a lot of packets and independently routing each packet on each independent route. So with this solution and this mathematical formulas, a very easy congestion related, a very easy congestion routing, we are enabled a very even more balanced network. And also we have a lot of cross-process fairness. So currently we are also enabling multi-tenancy on our network. The tenancy are not only used by one kind of network. We are using it for PD desegregation, for KV cache aware, and also EP. So it is used on different cases by different users. So we need to enable fairness, and we need to enable some certain level of multi-tenancy SLO guarantees. And also at the list things that we last but not least is that we need to enable self-healing. So currently, if one network interface card, we can automatically fall back to other route. So this is again an implementation level of optimizations. And so even with all the RDMA network all the RDMA are not available to the inference engine, we can still fall back to TCP to continue the work. And the final result, we actually compare our next version of transfer engine with our original transfer engine, and also another counterpart, which is the NVIDIA Nixel. As we can see that with all these optimizations, the throughput is better. This gain in throughput is mainly by the per packet dynamic spreading and the independent routing. And also we enable a lower latency, larger throughput, and we are extending its use case, not only in the inference, but also in the reinforcement learning. You know that currently reinforcement learning have training stage and the inference stage, and it will need to transfer the large model checkpoint from the training servers to the inference servers. And this transferring also are very bandwidth bounded, and our transfer engine next version can be much higher, can deliver much higher throughput in this scenario. So all these, all our work are based on open source community, which is the kvcache.ai and the Mooncake community. So if you are interested in the discussion or contribution, we are welcome to come to our community. Thank you.
Thanks very much. Great talk. Okay, we do have time for questions. I know that's a lot of stuff to digest, but I think there could be questions. If not, I have one to start off. So you mentioned your new development, the new technology for the unified system. So I know there are like other industry solutions these days, like unified bus. You probably have heard about this. How does it compare to that?
Yeah, actually, I think that a unified abstraction is used to abstract away all the difference of the providers. And the reason that why we build a new abstraction is because we call it the zero copy properties. We do not want a lot of layers stacked. We want only one layer. So we build it and we directly use it so that we can make best use of the zero copy. So we borrowed this idea from existing solutions, but due to the implementation, we need to rebuild it again.
I see. Quick follow-up. So you mentioned multi-tenancy as one of the objectives. So are you considering TCP at all, or do you think then we need other protocols for that?
Currently, we are using most of the network are transferred by the RDMA. So in terms of multi-tenancy, it has two scenarios. The first is even in one tenant, in one serving of the model, we have three different kind of use case, and we need the priority. For example, the EP traffic must be the highest property because it is latency critical, and the other are more bandwidth critical. So this is the tenancy in a single user. And the second is we are currently serving multiple models, and the different models will use different GPUs, and they will scale in and scale out. So this is the second kind of tenancy. But they all use the RDMA.
Okay, thanks. Okay, we have Dave in the queue.
Yeah, thanks for super interesting. I'm Dave Plonka from WISCnet. There was a lot to take in. I was fascinated by the part about the NICs and RDMA and kind of building up. It was kind of like bigger, better, faster, more for everything in the data center. And that seems good for lots of workloads, not just LLMs.
Yeah.
Did I understand correctly that what this is targeted to is this KV cache layer that all LLMs will be advantaged by? That's the first thing I was wondering. And then mapping it into the IETF, or what the IRTF might do, is the RDMA you're talking about all Ethernet, or does this map over to something that's in the IETF domain clearly that you suggest we focus on for workloads that could be wide area as well?
Yeah. So for the first question, we are actually the so-called KV cache centric architecture are proposed by us, and you know that essentially PD desegregation are transferring KV cache from prefill to decode, and the KV cache we use is of course centralized to the KV cache. So KV cache is one of the most dominant payloads that will be transferred around this kind of GPU data center, and the second is the model weight. So currently, transfer engine are used to transferring the model weights in the reinforcement learning scenarios from the training stage to the inference stage. And once the third glowing in scenario is the activation engine, and which is used for stabilize the IO inference. Typically, we need to transfer more information from the not only the weight, but also, for example, the activation that used in the produced in the training to the decoding to enable a more stabilized IO inference. And the first is currently we are exploring the CPU checkpoint, because we are now serving a lot of CPU agents, CPU agent harness, and they need to halt, resume, and scale. And this also leads to the scaling of their state, the CPU DRAM state for this CPU harness. And this part, we are also using the transfer engine. So essentially, transfer engine is a transfer engine that make best use of the high bandwidth network. And currently, we in different kind of scenario, we need this kind of high bandwidth. So we explore the applied scenario of this transfer engine. So this is the first question. And the second question, I think actually, even though that at the beginning, transfer engine is designed totally from a distributed system view, we are very high level. But currently, we are more and more related to the low level hardware properties, the RDMA, the InfiniBand, and for example, the priority of different kind of network flows, and how we can have a better telemetry about the workload, and the availability. And as you can see, we try to learn many ideas, such as the packet spraying, the per independent routing. All these ideas are well established in the original network community, and we are just rebuilding it in our transfer engine. And maybe some of these properties can be integrated or adopted by the network protocols, and we can have a better core design. I think that the current era is an era of core design. Our system is core design with the algorithm, and the system is core designed with the hardware. So there are a lot of future directions.
Oh, thanks so much.
Thank you.
Okay, we have Xinjiang in the queue.
Hi, can you hear me?
Yes, we can.
Okay, thank you. So a question about for the KV cache application, do we considering about network awareness and also the collaborate between, for example, the traffic priority and the congestion control during for the KV cache?
Yeah, actually, I think that the congestion control become more and more important, and because as I have mentioned, I'm from a distributed system team community. So originally, in small scale, we are not aware about the congestion. So the first version of transfer engine are not aware to the congestion. But now with larger deployment, we found that the congestions always lead to some P99 latency, high P99 latency, and that is what we are working on today. And especially for the EP traffic, it is very latency critical, so the congestion become a very important problem. And one of the reasons is, as I have mentioned, the bandwidth bounded traffic mixed with the latency band centric traffic. So this it become a reason of the congestion. And the second is the struggles in the network interface card. Periodically, we can find some of the network interface card are not transferred as fast as others. So this is the second source of the congestion, the stragglers. Yes.
Yeah, thank you.
Thank you.
It looks like we have one more question.
Yeah, thank you, Mingxin. And I have a question. Previously, we are mainly discussed about the inference scenario, right? And I'd like to ask about the new challenge and the opportunities in the agent era. So what will be the new challenge faced by the KV cache in no matter agent serving or agentic RL? Yeah.
Yeah, I think that the basic problem is it become larger and larger. So you know that when we become reaching the limit, all the problems become, all the small problems become bigger problems. Originally, as I have mentioned, currently the average context length become 64K. And it is growing to 100K. So the size of the KV cache are become larger. And originally we only keep KV cache in the DRAM. Now we are exploring SSD. And you know that the SSD become a totally different problem than the DRAM. How to manage the I/O, how to manage the latency, and the management become a more important problem. And also the problem become that it is not only originally reusing KV cache is always better than recomputation the KV cache edge. But now, because the KV cache become much larger, and if your KV cache are evicted to a code layer, such as the SSD, and if you have a very strict TTFT SLO, maybe you need to choose to be computation in order to meet your SLO. So decision, the scheduling become even more harder than before. So when the size is growing, I found that the problem become larger. And again, we now have multi-node NVLink. How to handle it? How to manage it with the RDMA? In which part we should use multi-node NVLink? In which part we should use RDMA? And even in China, we have maybe 10 different kind of GPU vendors. How you manage this kind of complexities is so all these problems become a problem in the current era.
Thank you. And I come from Huawei, and our team is really working on towards this topic, and I think we can discuss later. Thank you.
Of course.
Okay. Great. Yeah, thanks very much again, Mingxing.
Thank you.
Okay, moving on to the next talk. Let me. There's some mic echo hiccups at the moment. Okay. Okay, so yeah, we are delighted to have Hong Xu next. He's a professor at COHK over in Hong Kong, and he will talk about reliability engineering challenges in networking for AI. Hong, you can control the slides on your side with your cursor keys. Welcome.
All right. Can you guys hear me?
Yes, we can. It's quite loud.
Okay. Okay. Thank you for having me here. This is actually my first time joining IETF and IRTF. So I'm going to talk about a topic that's a little bit different in terms of the focus. So instead of talking about performance, efficiency, and so on, I decided to talk about reliability engineering, focusing on networking, but also actually in general infrastructure for AI workloads. All right, so in terms of the networking infrastructure for AI, as we all know, there's a lot of rapid development in the space. So if we look at like different levels of this networking stack, there has been a lot of innovation in terms of the hardware and also software technologies. So like at the server level and also the rack level, we've seen a lot of new things in terms of the interconnect technologies. So at the server level, we have things like CXL and NVLink and Unified Bus and so on and so forth. And at the rack level, we also have SuperPODs using these various interconnect technologies from NVIDIA, from Huawei, and also some open interconnect standards. So at the cluster level, in terms of the networking fabric, there has also been like some innovations in terms of integrating optics, which is really becoming necessary when we're going for high bandwidth for transferring all the models, weights, and KV cache and so on and so forth, right? And most most critically, the kind of the scale of our infrastructure for not just networking but also for other part of the AI infrastructure is really huge, and that's really becoming a problem for not just performance and efficiency but also for fault tolerance, for reliability, right? So we start to see that there's a lot of focus coming out of industry that try to look at, for example, training GPU training over 100,000 GPUs, and then how to handle the fault tolerance from the framework, from the training framework sort of perspective, right? So all of this is basically kind of the background that sort of underpins the importance of reliability and also how we solve the reliability challenge. So so basically, essentially, there are kind of three main things that make reliability especially challenging in terms of the AI workloads. One is the scale factor that I just mentioned. And also the other thing is that the complexity of the infrastructure, not just the hardware technologies, but also because we are going more and more towards the co-design kind of approach. So we're not just, when we have a new hardware technology like unified bus and so on and so forth, we don't just develop the hardware technologies. There's a whole software stack and there's a whole sort of ecosystem that's designed around the whole thing. And there are even like a lot of upper layer sort of technologies at the machine learning systems or machine learning frameworks kind of level that try to do a lot of innovation for various reasons. So as Ming-Xin just mentioned, when they're designing their new generation mooncake transfer engine, they want to sort of dynamically bind or utilize different interfaces, different networking stacks for various purposes. But you can imagine that with these type of like crazy sort of tricks and technologies going on, then the complexity of maintaining this kind of software hardware stack, and when there is a failure, how do you exactly pinpoint which part in this complex software hardware stack is actually causing the problem? So that's going to be really, really challenging. So that's reason number one. That's sort of also challenge number one. And the reason number two is that all of the training and also even all of the inference workloads, especially with agents and so on and so forth, all these workloads are highly distributed, and they are distributed over an increasingly large scale kind of number of GPUs and also networking links. And so when this just means that whenever we have a small hiccup that causes the job to maybe restart or partially restart, then that actually causes a huge financial cost. So we would really love to minimize this sort of downtime and being able to actually fundamentally resolve the problem, the root cause of the problem. And so the third kind of a reason why reliability challenging is especially reliability engineering is especially challenging these days is because the kind of the practice, the mainstream practice in terms of root causing or diagnosing the problem and then resolving the problem is still heavily a manual process. And so it's obviously very tedious, and fundamentally it's just very difficult for us to keep up with all these rapidly evolving landscape in terms of both the hardware technologies, the software stack, and also various things that are happening at even the hardware layer that try to actually being more aware of the infra and then to do all sorts of things to optimize according to the infra. Right? So on the right, you can see this is actually a statistics of different types of instances that we were able to collect from some GPU clusters at Microsoft Azure. But this was during 2023 to 2024. So it might be a bit different from the current situation now, but you can see that there are various types of instances that are reported by customers running the AI workloads. And a lot of it is related to GPU, but a lot of it is also related to software and also networking as well, and other components. So basically, in this talk, I have to kind of share and also sort of pitch our vision towards this autonomous kind of framework in order to perform troubleshooting and diagnosis for infrastructure, for AI infrastructure. So basically, the overall vision is very simple, which is that we want to build a agentic framework. We want to build sort of like an open cloud kind of system that can manage the NetOps or the entire AI infrastructure in terms of diagnosis and troubleshooting. So in order to realize this vision, I believe there are three fundamental reasons, and I sort of want to explain what are these challenges and then how potentially we can solve them. But a lot of it is still kind of not very concrete. So there's a lot of undefined things here, which is sort of the reason why I want to talk about it here. So I hope more people can join forces here and then discuss about it. So the most basic or the most essential challenge towards this vision is basically evaluation, in my opinion. So if we want to have a system or an agent, right, that can automatically troubleshoot incidents, we need to provide a reproducible and comprehensive and scientific kind of way that can systematically measure the effectiveness of such kind of system. And so that is essentially quite lacking, in my opinion, currently. So I'll talk about it a bit more in the next slide. And then once we have such kind of evaluation framework, then we can move on to question number 2, which is how do we design such an agent? How do we engineer the workflow of such an agent so that it can handle various different types of instance? And then when the instance is straightforward, then we don't have to think too much about it. We can even do just simple pattern matching, probably. But then when the incident is indeed a very new incident and involves different parts of the software and hardware stack, then we have to actually spend a lot of time thinking about it and then do a lot of real work to pinpoint the problem. So that's really challenging to me. And so that's the second part. And the third part is basically the system part. So once we sort of figure out how the agent, how the design paradigm should be for the agent, so basically we move on to the system part, which is how can we serve and how can we run this agent efficiently and also reliably. So basically, we think there are these are the kind of potential solutions that we can use in terms of answering those 3 questions. So in terms of eval, we believe that it's very essential that we have some kind of open arena, which is very similar to like LM arena or other kind of open arenas that we have for the models themselves, but this time for agents for NetOps or AIOps. Right. So we want to build sort of a open system that can reproduce, that can inject and reproduce all sorts of failures and incidents, so that we can do standardized and reproducible benchmarking. And so that essentially is what the eval challenge wants to solve. And to be more concrete, so there are a couple of smaller but still critical questions here, which is, first of all, if we want to have such kind of arena, then we must have a data set that are realistic, that comes out of the realistic infrastructures and also data center networks, and covers various kind of problems. And then we can use these data sets to inject failure, right? So that's our first kind of problem. And the second problem towards this task is that we also need to build an environment so that the agent can actually play in this, interact within this environment. And then when there's a failure injected, then the agents can observe and agents can do troubleshooting in terms of invoking different tools and scripts and so on and so forth on the hosts and on the switches and on the other parts of the infrastructure. Right. So that itself is actually a very difficult kind of system kind of task. And challenge number 3 is that we also want this arena to integrate the production tools that we have been using for a lot of time. Things like PinMash, things like Mycroft, which is another system that we developed with ByteDance for tracing collective communications. And there are a lot of other troubleshooting tools and monitoring tools that are already deployed in force. So we want our arena to be able to also invoke those services as well whenever needed. So that's the first part, right? First challenge. And the second challenge is the design paradigm for the agent. Basically, we're trying to answer the question of how this agent how the workflow should be designed. So I think at least there are three kind of basic questions here. One is that we have to really look at the context lens problem and handle it. Otherwise, this just simply wouldn't work. So if you imagine that we're dealing with a difficult problem, then there has to be a lot of troubleshooting, and then we're collecting a lot of data from all kinds of logs, all kinds of systems. We're looking at various metrics. That's a lot of context. Only a small part of that would be useful at the end, but we don't know. So if we just blindly feed these data as context to the model or to various agents, then it wouldn't be very efficient and wouldn't scale. So how do we actually solve this problem? And problem number two is basically the reasoning part, essentially how we should design these agents so that they can actually think about it sort of corresponding to the difficulty level of the problem, right? So like I said before, if the problem is quite straightforward, then you don't have to spend a lot of time. But if the problem is indeed challenging, then you might have to go through a lot of effort. So you have to you can think about whether you want to design the agent to work sort of sequentially in terms of how it reasons the root causes, or whether it wants to think about things in parallel in terms of I can think that there are three potential hypotheses for this problem. Maybe I should go out and then verify each of these independently in parallel, and then and even when I'm checking the network, for example, I can check various parts of the network sort of independently in parallel to speed up the process and so on and so forth. So that's number two. And then problem number three is that when we are dealing with instances, especially newer instances that don't come up very often or haven't come up very often, and it starts to emerge due to new systems and new hardware, then we really want this AI, this agent system to be able to actually learn from some of the limited experience interacting with these incidents. So that's going to be really interesting also. Right, so the last part is the software system itself, right? How can we design a software system that supports this type of troubleshooting agents so it's more efficient and also it's more reliable? So you can imagine there are tons of open question here. And again, I just list three potential things. So one is, I think, is cross-model communication, which is actually quite fundamental to all kinds of agentic workloads, I believe. So when you have multiple agents and multiple models sort of interacting with each other as part of the entire workflow, right, to solve the problem, then you have to communicate across these models. And you can imagine that it's not just the context lens kind of limitation here. There's more fundamental problem here, which is that when you think about communicating across models using KV cache or using tokens, essentially, that's one potential way. But you could also think about other ways that don't really rely on the token or the embedding kind of abstraction, but using some other abstractions that only models can understand. So it's different than tokens, which are essentially designed for people to consume, right? So there's I believe there's really interesting fundamental challenges here. So that's cross-model communication. And a second issue is the robustness and also assurance of such a system itself. So you could apply red teaming sort of technology here to understand how this troubleshooting agent itself might fail. And when it fails, what should you do, right? And the third problem is also full software sort of dev and ops cycle support for this type of agents, so that we don't just run this agent. We can also support different functionalities such as versioning and testing and the rolling back to a particular older version when things don't work out and so on and so forth. So when going for production, these kind of things would also matter a lot. Right. So I've talked about a lot of open challenges, and then in the remaining time, I sort of just want to briefly talk about some of our work that kind of try to make some progress towards this vision. So we've done a few things. One is about the open arena, which I just talked about. And so we're basically, this is still ongoing work. We're working with some of the biggest AI companies, collecting data and trying to build this open arena that can inject failures and so on and so forth. So that's an ongoing work. And we've developed a TS Guard, Troubleshooting Guard, which is going to appear in FSE this year, a software engineering top conference. So this talks about a user-centric troubleshooting agent for AI workloads. This is joint work with Azure. And we've also deployed a system called NetOps AI, which is also a troubleshooting agent, but targeting networking and networks. And this has been running at a leading company, AI company in China as well. And finally, I'll briefly introduce Mycroft, which is a tracing tool that we deployed and running at ByteDance for collective communications. Okay, so I'll be quick. So first about the TS Guard. So this work really started a couple of years ago. Actually, it started in 2024 when I was doing sabbatical in Microsoft Research. And so we had this idea, which is try to see if LLMs can help us troubleshoot all these instances coming from Azure's customers. And we want to particularly focus on their AI workloads and AI infrastructures. So that's essentially the motivation for this work. And because of some limitations working with Azure, so at the end, what we decided to do is sort of the user-centric kind of agent, which means that what we can do is only for the agent to observe the incidents that are reported by the customers, but we are unable, for our agent is unable to directly interact with the infrastructure. So what we're trying to do is just to, based on the incident report from customers, we do a diagnosis and then try to make some educated guess about what the root cause is. And in terms of our design, we adopt a two-phase approach, which is pretty intuitive, I guess. One is an offline knowledge building kind of process to build the foundation for the agent, to build the brain for the agent. And the phase two is the actual online troubleshooting phase. And so in the offline case, basically, we look at this 1 year period of incident data, like I showed you before. And then we basically derive a taxonomy in terms of structuring all these different possible types of incidents that we've seen in the past, and the root cause, and also essentially how to deal with each of these types of incidents. And we also add some domain-specific rules and knowledge that are specific to Azure into this taxonomy. So that becomes our basis for phase two, the online diagnostic. So the diagnostic system part basically is designed around a tiered kind of a heuristic. So what we're saying here is essentially, first of all, when an incident comes up, we will really quickly run a sort of pattern matching kind of workflow, and then try to see if this is a recurring incident that has been observed before, and then we know how to handle that. So that is resolved using RAG and other technologies. And once we found out that this is not a recurring incident, it's a kind of complex incident, then we will move to, which is the slow path. And then the agent will step by step try to systematically come up with different guesses and then verify each of the guesses in terms of what the problem really is. And then during the process, it could deploy various benchmarking tools. Although, like I said before, we can't actually experiment that on Azure directly, so we were experimenting that in an emulated environment. And so the last tier 3 is that when we've seen a incident that's completely new to us, then we would spend even more time and then come up with various possibilities and then evaluate these possibilities even with more time. Right. So essentially, we evaluate such a design against various baselines at that time, and we were able to show that essentially in terms of the F1 score and other things, TS Guard can achieve much better diagnostic accuracy in for various types of incidents. right? And so the second kind of work is the NetOps AI, which is basically a deployed system running in a leading company. So the figure is not a real screenshot of the system because we were not allowed to do that. So the figure is actually generated by AI, but based around the same idea. And basically, we want to show you what kind of things this system can do nowadays. So it's actually more than a troubleshooting AI. It's more like a portal for NetOps. So it integrates a lot of functionalities like metadata query, depending on the context. So you can query about various parts of the network directly, sort of just, it's like interacting with LLM. And you can do end-to-end diagnosis as well. You can do telemetry analysis, and also you can do other things, right? So we will try our best to try to collect some data and then try to write up some technical report about experience of using the system in production, but that is still ongoing. And the last work I want to share is Mycroft, which is also about reliability engineering. So it's more about building an actual tracing system as part of the infra so that we could provide more information about what went wrong. And this is mostly focusing on training. Okay. So essentially what Mycroft does is that it provides fine-grained tracing abilities for collective communications. By collective level sort of tracing, we mean that in Mycroft, it is able to provide the real-time logs that are generated periodically, especially when a collective communication remains unfinished. So previously, a lot of these tracing tools will only give you things like timestamps when the operation finished. But if the operation cannot finish or is stuck in the middle, then you won't be able to get anything. And so this is Mycroft is different in terms of it's able to actually give you real-time progress kind of logs, even when your collective communication is stuck. And then with this kind of fine-grained information, then you would be able to detect problem a lot quicker, and then you would be even able to detect the potential root cause of the problem. So that's what Mycroft does. Okay? And so this has been running since October 24, and we were collecting data for 2 months period of time. And so basically in the SLSP paper, we reported a lot of experiments and also a lot of data. But here, essentially, I just quickly show you like the trigger time and also the root cause analysis time distribution for this 2 months period of data that we collected. And you can see that we were able to perform over 1,200 root cause analysis, and 90% of these problems were detected within 15 seconds of onset, and 60% of these analyses are completed within 20 seconds. So that's very efficient. Okay, so that's everything I want to actually talk about. So basically, I believe it's a great time to work on reliability engineering for not just networking actually, but for the entire AI infra. And we'll welcome all sorts of discussion and collaboration. If you're willing to actually share some of the data sets regarding incidents and failures, we would love that. Right? And so, yeah, so just before I close, just want to quickly mention that actually in yesterday's one of the sessions, my student gave a talk about our other sort of project, which is about network configuration management based on LLMs. So if you are interested, please also check that out. All right, thank you.
Great stuff. Thanks very much, Sean.
Thank you.
Let's see whether there are questions. And I have Rod in the queue.
Thanks. This looks like really good work. The one thing I didn't get from the talk is what the overhead is on the production systems themselves for the monitoring and tools that are actually used for this.
So you mean the things like Mycroft and PingMesh and
Yes, yeah, the whole set of things you talked about. You talked about 3 different things, and you talked about the computational cost of doing the analysis, but you didn't talk about the cost of actually collecting the data.
Right, I understand. So in terms of these individual systems like PinMesh, like Minecraft, their overhead is actually quite small. So for example, for Minecraft, actually, I don't have the slide here, but on the paper we were showing that its impact to a training job is very minimal. It's like less than 1% in terms of the additional latency overhead. And the Minecraft system itself is actually just running on a server, and then and it's seeing a lot of data, but in terms of the actual resource that we need to spend processing these data, I think it's quite the overhead is not that big of a problem. But in terms of the entire if you're talking about the entire like agentic system that will process each of these instances, I don't have very concrete data about that overhead. What I know is that you have to provision some additional GPU servers just for those agents. But yeah, but I think the overhead is not a huge issue over here.
That's what I was expecting. I was just wondering if there was something you weren't saying. So that's actually really encouraging. But what about the ability of the system to detect problems with itself, with its own monitoring tools and things like that? Can you do that as well with this data gathering system?
Right. That's a very interesting question. Yeah, we haven't tried that actually. So I believe we could do that. Yeah, I believe we could try that. Yeah.
Thanks. By the way, I love the picture on the whiteboard.
That's from my daughter.
Okay, another question, Roberta.
Hello, Professor. Thank you for the presentation. Hi. I have some questions related to security and also related to hallucinations. You're using CloudBot and you're using agents. I imagine all the agents that have been mentioned, they are generative agents?
Yes.
How are you dealing with the hard data manipulation that might, 13 to 17% of the times might happen because of hallucinations when they are reading hard data such as, log files, those kind of registries to be able to do the training. And also into your agents that you use to do like the troubleshooting and maybe regeneration. I'm imagining here from how are you circumventing this risk?
Yeah, great question. So obviously this goes for all agent workloads, but it's probably more critical when we are using agents for like maintaining infrastructure. So a lot of I think there's a lot of things that you could do to sort of safeguard and then alleviate this hallucination problem. So a lot of that comes down to how you build the so-called scaffolding or the harness around your agents, and then how you structure the workflow so that you can use like different paradigms like skills and other things. And when you write your skill, you can sort of try to mandate so that the model will have to verify all of the possibilities against benchmarking script or other data that it actually collects. And so I think a lot of that is quite helpful in preventing or like alleviating hallucinations, and that's also what people have been doing when deploying these kind of things. Yeah.
You're actually actively working on scaffolding for those cases, because what I've been seeing on research and seeing on presentations here are that people are, implicitly trusting that the scaffolding that exists is already good enough for taking care of some of those questions. But in security for defense, we have a really huge issue for, the problem dimension being infinite, because it's non-deterministic, right? So when you train an agent to scaffolding into one type of problem, one type of issue, changing just a little bit of that issue will, remains like infinite versions of the issue that might happen and trigger a response for the agents that it was not on the training, like the original one. So this is kind of, because it will solve a lot of issues that we have been seeing here. So this is why I was asking. I don't know if you can share it. We can talk later.
Right, sure. Yeah, so I'm less aware of the security side. I think so. I think basically there are, so in terms of troubleshooting here, there's a lot of additional ways for you to actually verify, even if the model actually hallucinates. So that could be sort of the last line of defense over here, but that is only for this scenario, for this particular task. Yeah.
Thank you, Professor.
Yeah.
Okay. Yeah, I have another question.
Sure.
So the open arena topic, so it's actually interesting. So we also had some previous discussions. So to what extent could test bed and maybe data sharing, data set sharing activities be useful in, let's say, an IRTF context? I just wanted to ask your opinion. I mean, often these data sets, are a bit difficult to share, right? So there's lots of privacy data in them. Do you see a chance for an activity? So test beds, data set sharing, like in an open environment, like the IRTF.
So I think this is really fundamental, and I mean, if we're able to put together such kind of data set, it will be really fundamental to research and to industry. So I think for IETF or IRTF, I think it would be possible to sort of come up with like a taxonomy kind of things, and so we have a way to like categorize all the possible like failures regarding networking. So maybe it's a switch failure, and in terms of switch failure, what essentially different types of switch failure versus host side kind of problems and so on and so forth. And then there's software stack problem and other. So I think it's possible to come up with a taxonomy first, and then with this taxonomy, then maybe it will be easier for different people, even companies, to contribute like incident data in terms of what is the failure pattern and how exactly the failure looks like. So when we are interacting with, of course, we're working with some companies, so they're willing to at least share some actual failure data, which they believe are actually quite common. So it's not really proprietary, so to speak. But maybe when it comes to other types of failures, so networking probably is easier in that regard. But then when it comes to other part of the infra, it might become more sensitive, so to speak. So I think for networking, it's probably, yeah, maybe the most challenging part would be things regarding IB, which is really a black box. And yeah.
Sure. Okay.
That's
Makes sense. Thanks very much. Okay, great. Thank you very much again, Hong. Great talk.
Yeah, thank you.
And now something different. So next talk will be by Lisha Zhang. And I don't have her slides on the data tracker yet, so it's not synchronized. Give me a second. Reload, okay, thank you. Yeah, click works. Yeah, just need to get the slides on.
Hello, everyone. This is Lisha Zhang from UCLA. I uploaded the slide late because we are doing research in real time, right?
And I don't get them here, but I can maybe share them for you. And then,
let me just get started.
Sure.
To talk about networking. This is 2026, exactly 40 years of the IETF activities. As I attended back in the 1986, that's the very first IETF. At the time, we were really struggling with just how we could interconnect all the computers together. I remembered those days, the two challenges are routing and then congestion control. The bandwidth was slow and the traffic grows exponentially. So therefore, on the first time you do anything, you don't know how to do it, and you learn through the practice. If you can turn into this display mode. It's
yeah,
okay.
I figured
okay, great. Yeah. So what we are doing today is we are networking AI agents now. So AI agents, I tell my students, is really the new front of networking. It's not like I get into AI per se. I'm still doing networking after 40 years. I really enjoyed the previous talk, talk about all these exciting new challenges, but also new results, how we move the AI forward. But like anything else, they need the networking. So networking people come here to help moving the AI forward. Now the question is that since both hosts and agents need networking, now what's new and what's the same? That's what I want to talk first. Then we identify new challenges. Oopsies, did I change it? You adjust it.
Oh, sorry, I was proactively changing, but.
Should I adjust it?
No.
Okay.
Give me the clicker. You can't control it.
Okay. So I want to talk about what's the new challenges in networking, and then just identify some things. Hopefully, we can all work together. This is IRTF. So I'm now talking about what we must do today. What we must do today is keep work going. AI is already there. Agents are already there. They are talking now, even though far from imperfect. That is many challenges. But meanwhile, the research community, we need to move forward to look further out to see how we can improve the current situation. Next slide. So talking about the networking, what do we do? Put plainly, we deliver packets. That's the bottom line of networking. But for delivery, there are different ways of delivery. People normally say one-to-many, many-to-many. I think AI actually put some things like I put there the I to J. I can be some subset of the entities on the network, and J is some other subset. And J could be the full set, otherwise could be part of that. So in the day one, because the TCP/IP was a point-to-point, that's what we do, and that's what we still do today, point-to-point delivery. And for the agent, I think we also started by the point-to-point communication. But soon in the internet, we needed to scale the data dissemination. Therefore, I remembered clearly in the late 80s, IP multicast got developed, intend to scale, say, the audio-video dissemination. Although in reality, IP multicast turned out to be a real challenge. It's another story I'd be happy to share for whoever interested exactly what happened. But what we now to support dissemination is actually through CDNs, content distribution network. Now, the AI also wants multicast support. How do we do that? Yesterday, I had some discussions with really the first-line engineers, and clearly people have different views regarding that. But nevertheless, talk about communication patterns. The pattern itself is not new. Now, I don't have to talk about the N by N, the N to 1. But generally speaking, is that what we do in practice is that we do multiple one-to-one communications to fulfill the need for I to J communication. That's just a matter of fact. If we move to the next slide. Now, what's another thing is not new is security. I must say that in day one, back in 1986, security, everyone knew was important, just that it wasn't the problem we are actively working on at that moment. These days, you hear the talks, people will start by saying that TCP/IP didn't have security design in, as if that's ignorance. And I really want to put that straight. It was not ignorance. My former advisor, David Clark, keeps saying that we were full mind of security. It's just that we didn't know what's the threat and what's the problem that we must solve today. That's how TCP/IP didn't start with the security. But very quickly, in the early 90s, e-commerce came online, and then people needed this security transaction yesterday. So therefore, some solution developed quickly, SSL with the web PKI, certificate authorities, this and that. Then, if I can see it clearly, then later, because money tend to bring evils, the spams, DDoS attacks, and all sorts of other things came along. And what we do is we just put kind of some kind of filter at all the different levels, firewalls, this and that, trying to block the attacks. So what we'll end up with is really different solutions at the different levels. And what we get today is a set of solutions. Do they interact? You know the answer, right? And sometimes they actually counter each other. I heard a story of some company wanted to deploy CDNs, not CDN, so sorry, VPNs for the enterprises. And one big hurdle they run into is a firewall. Because the CDNs, VPNs need to punch a hole on the firewalls at the cost of real engineer money, so they say, pay us for punching the hole on the firewall so that you can deploy your security solution called VPN. What I want to say is that the security is a late item, and then we don't really have a unified namespace to talk about what is the threat, who is the bad parties to develop some kind of collaborative solutions. And therefore, we ended up with this fragmented solution space. There's one thing I probably forgot to put into the slides. Let me add on to that. So IETF, now the IETF, TCP/IP started with just addressing. Back in 1981, when the RFC 791, 793 got rolled out, we just had IP addresses to deliver packets. At that time, there's no DNS yet. There's a kind of informal things going on. But if you look at the RFC series, the first DNS specification, I remember actually published in either 1983 or otherwise 1984. So DNS was added, at least the standard, late. Now, at the time, again, at the very beginning, all the hosts would get an IP address. So therefore, we have this statement, anyone can send packets to anyone else. But as this DNS came along, we somehow lost that. Who get the DNS names? Servers, websites. Do you have a DNS name? I think maybe 0.1% of you guys do, but the majority of us do not. Now, when you get into security, the very first thing is authentication, who you are. And that would lead to the second question, what you can do. Without a unified identifier space, that's how our security solutions get fragmented. Now, we all have security in the cyberspace. You log onto the web, you have single sign-on. What's your identity? Not the DNS name. Server authenticated by DNS name, not you. By and large, my personal understanding is that users identified by email addresses. Why email address? Because email address is globally unique, identifies you. It's really DNS name, just plus a little part. That's your user ID assigned by the email provider. So therefore, there is the implication. Who owns your identity? It's the application provider. So therefore, you do not have an application independent identifier. I just state that as a fact. If you go to next slide, I probably should go forward faster. Yeah. So what's really new? It's not communication patterns. It's not really no security. We do have security. But I go on to talk about what's new about agent communications. You can see that previous solutions for security really got stretched out. So these days, I keep inventing the triangles. Yesterday, I talked about for the internet naming, we have 3 requirements, the requirement triangle. What I put down here is actually the agent networking patterns or behaviors. Number 1, they need a scale. Number 2, they're dynamic. And then number 3, all of them together, is a multi-party interactions. If we follow our vision, make it true, it's really agents working together with each other. Now, let's go through all of them together. Talk about the agent scale. People say, we're going to have billions of agents, probably soon. Then we're going to go on to trillions. This sounds a very big number, but like I put in something there. Today's internet already have billions of human users. And in terms of devices, there's like 45, 50 billions already. So billions is not a big number in terms of networking. We do that now. Now what's new here? What's new here is the next 2. The dynamics. A user doesn't just show up in a minute and disappear again. Nor is any devices. But the agent can. The agent who's going to stay there for years maybe, but there will also be agent, it'll be so transit, maybe last at the sub-second level. And we do not really have a way to how we deal with this kind of agent, how we identify them, especially how we make that agent even last for 500 milliseconds, how we make that accountable for whatever the actions it performed during that short lifetime. The next thing is about interactions. Right before I went to the airport for this IETF, I had a dinner with a group of people who actually developed the AI agent for their application-specific usage. They need group agent communications, group communications. So they asked me, why this is hard? Look at us. We have groups in WhatsApp. Why can't you do it for agent? Why can't we do it for agent? Because users do not have direct interactions. As of today, we interact through the cloud. That's how WhatsApp groups work. But the agent cannot do this interaction indirectly through the cloud because they have real-time requirements. So therefore, you put all the 3 things together. I think all the 3 actually point to one point. We need to have decentralized networking, decentralized identity management, decentralized trust. I'm not saying that I'm the co-chair for the DNRG together with Dirk. I'm just trying to be objective, pointing out that Agentic AI will give a big push toward the direction to decentralization. From where we are today is more or less cloud-centric networking. Next slide. So I mentioned the 3 things, but then there are 2 more stuff that really further put the stress on the existing security solutions. The number 1 is the delegation chain. Me as the user will delegate the agent, you do this. The agent, of course, going to delegate to other agents for complicated works. Now, do we have the security solutions that support this kind of multi-stage delegation? Right. Another thing, together with the delegations, autonomy. You want the agent to do work because you don't do it. Agent gonna act on your behalf, but autonomously. And therefore, we still need them to be kind of accountable and how we make that work. So they no longer have this per action permission. And people say, let's do the tokens, okay? We have auth tokens, give each action a token, right? See if we can do that within that time limit and within that scale. I may be ignorant with the current solution practice in security. My understanding is that all the token servers are actually in the clouds. Now, so it's the order of magnitude requirements in terms of dynamics, in terms of interaction, in terms of scale, really says that. It may not be feasible. We just move on whatever we have today for the agentic networking. Next slide. If we remember what that is. Yeah. So I want to bring up another thing about the physical agent. This is because some companies came to me talk about that. They say that the IETF had a lot of discussions about agents, but seems it's all about the models, right? The language model agents. What about our need? We need the physical agents. Physical agents in the manufacturing floors, physical agents in hospitals. As a matter of fact, I heard that there's already deployment there. Now, what's different between the software agent and the physical agent? I listed a few there. Number 1, I use agent, but still one-to-one. Physical agent, I think by nature, they'll be multi-party. I talked to some manufacturers, they really want to turn all their current statically programmed robots becoming physical agents, so that they will intelligently working together, equipped with sensors, and also interact with humans. Then there's this real-time requirement, talking about interacting with humans, because if you get the time wrong, that can cause physical damage. And that's related to about the direct physical interaction. Think about you make a model call. It can be problems. Your call can be failed, but there's a software system fail. You say it can have huge damage, right? Your agent somehow behind your back gave, I don't know, $300 to somebody else. It is a big damage, but hopefully those soft damage can be fixed by the software system. Physical damage, on the other hand, is much more difficult to fix. If your robot just roll over something else and destroyed it physically, I doubt it could be easily fixable. So moving on to the next slide. Oh, so the next point is that I think the thing that I just put the highlight to say the agents, the scale dynamics, and the multi-party interactions really expose the structural failures of the existing security solutions. It's not the performance issues. It's not about your crypto, how fast you can run, issue certificate to agents, or maybe even revoke it, but rather it's really structural things that seems to be not promising direction to carry to this security solutions onto the agent era. So I give some specific examples here. Talk about the namespace. We dealt so far with humans. Okay, we get our email addresses. Do your agents get the email address? Probably not. You think, oh, we can give it one. Sure. Who? My email address, I get a Gmail address. Would you ask the Google, give your agent a Gmail address? You have to figure out something else. So it's the number one question, how you can name the agent? Today's stuff, right? You get all these solutions, the oaths, the SSH keys, the API tokens, all of that. Do they apply with all this kind of mixed identifier approaches apply for agent? We talked about agent going to interact. Today, I believe agent interaction is still within some scoped domains. But people imagine that tomorrow we're going to have inter-domain agentic communications. Now, how we deal with this identity issue? If your domain use something as identity that's different from my domain. Next thing about certificate, I already mentioned, you can run really fast to give everyone a certificate. There's a scale. We have today, how many certificate authorities? I asked the security experts, they give me some numbers, someone say 100, someone says 300, doesn't matter, some number of hundreds. Now, would these security CAs issue certificate to agents? You have to do something very differently. I'm not gonna go down to the track of certificate revocation. I think you can spend 3 days just talking about how well those solutions work. Now, the next thing is about this authorization. Now, we have single sign-on on the web. We got the token, and token give authority to, someone can access my, I installed new software. Gmail is my, the old server give me a token, so this new software can access some part of my data, right? But I question to say that none of the existing ones, combination of them, would be suitable to secure the agentic system.
Yeah, we have to move a little bit faster. We have to move a little bit faster.
Oh, yeah, sure. I'm done. Yeah, I don't know how many slides now. So starting point. Yesterday, we have a joint talk with Dirk about the why naming matters in this future kind of integrated AGI era, where we talked about that you want to fix the security problem, you want to fix the scalability problem. Let's start with fixing the naming problem, so that we advocate this notion that DNS namespace should be serving as a unifying namespace for everything. It's not just for organizations. It's not just for applications. Today we don't. We have websites, but organization users, applications, agents as well. This unified namespace will provide you the foundation for you to talk about security. Who is who and what this guy can do. So name alone is not enough. DNS name is very meaningful. UCL.edu, you know what that is. But you cannot say, I prove this is my name. You have to combine that with crypto. So identity is your name plus crypto certificate. Now, who gave you that certificate? Let's get into the trust anchor question. Today, we get a certificate by and large from the CAs. And tomorrow, we really promote this direction. Like earlier said, this triangle all point to decentralization. We need to have decentralized trust management. Go quick. Okay. So if we want to get there, start with naming and start with decentralized trust. We need to build the tools, new tools to do that. Today, we don't have the tools to support the notion that you get a name, you have the automated tool set to help you manage the names. I can easily get a name from our department, lisha.cs.ucle.edu. If I give these names to 10 servers I don't know how to manage it. I don't have tools for that. Especially for agents, I fire off 20 agents. Someone lives for 3 months, other one lives for 3 seconds. I don't have tools to manage that. And associated with that is really this decentralized trust management. We're talking about certificate. They definitely need a certificate issued by me if I'm their owner. but I manage that certificate, not myself, but automatically and yet securely. And this really points to the next one. So 3A's, this notion of authentication, authorization, audit for accountability has been lived for over 20 years as far as I have learned about this word 3A's. But in reality, we don't really have a principled way to realize it. And latest time, if we want our agentic AI dream to become true, we need to put that into reality. Now, next slide, I think is my last one. Call for action. We are the IRTF. I said that IETF can standardize protocols quick because agent communication is there. We need something to at least guide the common practice. But for IRTF, we need to look into the next N years, where we want to be. If I convince you, applying what we have today wouldn't last us into the future as we imagine. Now is the time, if not late yet, to start looking for the direction for the new solutions. I will skip the detail, and then, oh, this is my last slide. No, this is the last one.
There's more, but if you want to
go. Yeah, I think all of this I mentioned already. DNS, localized trust, and I think only one thing new is about we need to engage the regulatory body early on about how agentic AI should be regulated before the current market force actually influence the regulations too much. Now, take away this summary. Agentic networking, we need to start with the global naming, semantically useful DNS names, and localized trust. So what's new here is not one-to-one, one-to-many communication. What's new here is a special requirement to support agentic networking. And then today's collected security solutions wouldn't carry us far enough into our dreams. So therefore, we need to start a new solution development. I already mentioned about two suggested research investment. We really should get started quick. Then I think I just ending slides to say that agentic AI, agentic communications is really new front of networking. And this is really a good opportunity for us to start from the ground up and trying to build the things. I mentioned before, today's system is where we are because we started with an entirely different world. It's just when I started, a few thousand machines probably worldwide. Today, it's a totally different world. So far for 40-some years, we just build on top of the foundation, address-based communication, add things as we needed. Agentic AI gave us a strong push to say, can you still live on these incremental changes? And that's the big question. So we can discuss the answers.
Great, thanks, Lisha. So on that inspiring note, do we have questions for Lisha?
No questions.
I think people need some time to digest.
Hi, thanks for the talk, Arthur from Huawei. So one question, so security is nice, and we don't have enough, I understand this, but it's also a double-sided sword, right? Specifically when it comes to agents, which might act on our behalf, so your behalf, on my behalf. If we scrutinize everything, isn't it some kind of global surveillance where everything is accounted for and, you know, anybody can see what my agent has done on my behalf, where exactly, how the traces are left everywhere. So where is the limit to all this? Thanks.
I think that's why, if I get your questions right, that's why semantic naming, like DNS, is so important. The name, you can see that there's a few layers of hierarchy define the scope. You can utilize that to decide my agent, who can see it, who can communicate with it, by defining your security policies. Security policy, by the way, I rushed over, sorry. It's something new we don't have. Do we have security policies today? Yes, we do. That's how we issue tokens. We give permissions. Where do those policies live? That's the question. In your head. Again, I'm not in this industry. I talked to some industry people. They were saying that backend, we have this gigantic table. User ID, permission. That's your policy. With agent communication, that wouldn't work. We need to develop really security policies, just like, I used to be a routing person. I'm not promoting BGP policy routing, but I use that as an illustrative example, right? When you do the routing reachability propagation, there's actually policies guarding or filtering what prefix propagates and what not. This is not the table, this is by rules. I'm not saying BGP had good rules, I just use that again as an illustrative example. And security built on the semantic hierarchically structured names will be able to help you build automated security policy solutions. For anyone interested, I just total full disclosure. I've been working on named data networking since 2010. And that's what we have been doing. Essentially build upon the DNS names and develop automated security policy decisions so that people define policy, the system will execute automatically. Whoever interested, contact me for details.
Let's take the next question. A quick reminder for people in the room, if you want to ask a question, please use the Meet Echo queue system. But next we take Wes online.
Actually, it's not Wes, it's Dave. Wes is running the remote room login.
I see, okay.
So I may have vastly misunderstood some of the things you were saying about naming. So let me sort of propose what my understanding is that you're proposing that agents have their own naming structure. And what I wonder is, isn't it a whole lot simpler if agents operating on my behalf operate with the names associated with my own identity rather than some independent identity? And doesn't that sort of factor the whole problem out in a much cleaner way? So explain why I'm what I'm misunderstanding here.
We say that agent actions need to be accountable. Now, who is that party behind the agent? Take that accountability. That is the question. Whether it's your identity or somebody else's identity you can use for that accountability, that'd be your answer. But fundamentally, you need this authentic identity for accountability. Exactly, that's yours, others, your organizations. Those are the implementation details.
I don't see them as implementation details. Okay, thank you.
Great, okay.
Policy details.
Thanks very much, Lisha, again. So we took a bit more time for the discussion after the talks, and we didn't cut this short intentionally because, well, the discussions were very good and also led to many insights on potential topics for internet research. So I took some notes and just wanted to check whether I got everything. So we talked about test beds and data sets, right, in Hong Xu's talk. And so that is a topic that was brought up previously as a potential good activity that like IRTF, group or activity could well do. We talked about all these new system designs at the intersection of distributed computing and networking. So KV cache-centric systems, unified protocol or unified abstractions. Then just now we talked about different agent communication patterns. So group communication, low latency, interactive communication, and then very important topic that was brought up was the whole security, so naming, identity, trust delegation for agents, and also preparing for a world where the scale that we are now used to would be challenged in terms of dynamic instantiations, dynamic coalition forming between agents. And so these are what I think, these topics have all quite good potential for, really good research that would go beyond like the current, say, protocol engineering aspects that are discussed in, let's say, in the IETF. So what I will do, so we have another IRTF open session tomorrow at 2 p.m., the first afternoon session. I reserved some time for continuing this discussion. I tried to get a summary of today's meeting and present that briefly, and I hope people who are interested could come to that meeting and then continue the discussion there. So I'd like to thank our speakers and everybody who participated and everybody who came today. Thanks very much. Meeting adjourned.